Welcome back to Quiet Science Journeys. Tonight, imagine a perfectly round circle of darkness not painted onto the sky, but carved into it as if space itself decided to hold its breath. You are safe where you are. Nothing in this story is coming for you. A black hole is not a roaming threat, and it is not nearby. It is simply a faraway place where gravity becomes so strong that light cannot find a path back out. Most videos meet black holes with fear, as if the universe is trying to scare us awake. Tonight, we will do the opposite. We will meet the same reality with calm and let it settle your mind instead of sharpening it. If you have seen dramatic headlines or fast edits or the word destroy flashing across a thumbnail, you can let all of that drift away now. Black holes are extreme, yes, but they are also steady. They follow rules, and rules are comforting because they mean the universe is not random even when it is strange. For a moment, notice the room you are in, the air against your skin, the weight of your body where it rests. Let your shoulders soften. Let your jaw unclench. You do not need to brace for anything. In this journey, facts will arrive like soft footsteps, not like alarms. When we reach something uncertain, I will say so. When something is well understood, I will anchor it gently. And if any detail feels too sharp to hold tonight, you can set it down. You will not lose the thread. I will keep it for you. A black hole can sound like a hole in space, like a trap door. But it is better to think of it as a boundary, an invisible shoreline in the fabric of the universe. Outside that shoreline, light can still travel outward. Inside it, every possible path bends inward instead. That simple idea holds a lot of quiet wonder. It means the universe can curve. It means time can behave differently under gravity. It means a place can exist where the night is not empty but deeply shaped, and still none of it threatens your night. So let's begin gently with the view from far away. Not the panic, not the myths, just the calm shape of what a black hole is and what it is not. Tonight's journey has a simple shape, and I will keep it slow. First, we will stay outside the black hole in the region where our eyes and our instruments can still learn something. We will talk about why a black hole often appears as a dark center with a thin ring of light, and why the sky around it can look subtly distorted. Second, we will move closer in imagination to the edge called the event horizon. We will understand what that boundary really means, why it is not a solid surface, and why it marks the point where light cannot return. Third, we will let our curiosity touch the strangest part, the way time behaves near a black hole. We will see, in a calm way, how gravity can slow clocks, and why different observers can honestly measure time differently without anything breaking. Then we will step back and widen the view. We will compare different kinds of black holes, from the smaller ones left behind by dying stars to the quiet giants that live at the centers of galaxies. And we will briefly glance toward the extreme end of the scale, the kind of black hole so large it makes our usual comparisons feel small, not as a spectacle and not as a scare, but as a reminder of how wide the universe's range can be. Finally, we will touch the questions we do not fully know how to answer, yet the places where our understanding becomes incomplete. And we will hold those questions gently without turning them into dread. The unknown is not a threat. It is simply the edge of a map still being drawn. You do not have to hold this plan in your mind. I will hold it for you. You can listen with half attention. You can drift in and out. You can fall asleep at any point, and the story will keep moving softly beside you. If you remember only one thing tonight, let it be this: a black hole is not a monster. It is a place where gravity becomes so strong that the universe draws a boundary, and beyond that boundary, light cannot return. And everything else we explore is simply the gentle unfolding of that one idea. So take one slow breath, let it out without effort, and when you are ready, we will start with the calmest view of all. From far away in the quiet dark, a black hole does not look like a hole. It looks like a shape in the sky, a circle of darkness wrapped in light. From far away, the first surprise is how quiet a black hole can look. It does not glow on its own. It does not shine like a star. It does not flicker like a comet. If a black hole were alone in perfectly empty space with nothing around it, you would not see it at all. What you see instead is what surrounds it. A black hole is revealed by light that almost escapes. Picture a cold, dark ocean at night. If nothing moves, you cannot see the surface. But if moonlight catches a wave, the wave becomes visible, not because the ocean changed, but because light met motion. Around a black hole, the waves are gas and dust, matter drifting through space thin as smoke begins to fall inward, not in a straight drop, but in a spiral. That spiral is important. Most things in space are moving even when they look still. Gas clouds rotate. Star systems orbit. Galaxies turn. So the material that approaches a black hole usually arrives with sideways motion, with angular momentum. It cannot fall straight in. It has to circle as it descends. As it circles, it rubs. Tiny particles collide. Streams of gas shear past each other. Friction builds not like rough sandpaper, but like layers of fluid sliding at different speeds. That friction converts motion into heat, and heat becomes light. This is the beginning of the ring. Astronomers call it an accretion disk, a rotating disk of hot matter spiraling toward the black hole. You do not need the name tonight. Just feel the image. A dark center. A bright, thin swirl of matter around it. Light made from motion, turning in the dark. Now here is the next surprise. If you look at an artist's drawing of a black hole, you often see a neat ring and a clean shadow. In real physics, the light is not arranged like a perfect necklace. It is shaped by gravity, and gravity is not just a pull. Gravity is curvature. Near a black hole, space is curved so strongly that light changes direction. Light does not like to be told where to go. It travels in the straightest path it can. But in curved space, the straightest path can look bent to us, the way a straight line drawn on a globe curves around the sphere. So the light from the hot disk does not simply fly outward in straight lines. Some of it is bent around the black hole. Some of it is redirected toward you from the far side. Some of it is curved into arcs and loops, as if space is quietly folding the view back on itself. This is why the black hole can appear to be wrapped in a ring, even when the disk is tilted. You might be thinking, why does the ring look so bright on one side in many images? That brightness is another gentle consequence of motion. The disk is rotating. One side is moving toward you. The other side is moving away. When light comes from a source moving toward you, it can appear brighter. When it comes from a source moving away, it can appear dimmer. This is called relativistic beaming, and you do not have to memorize it. Just notice the feeling. Motion changes light. Gravity bends the paths. And together, they paint a ring that is not symmetrical in brightness, even if the underlying structure is steady. Now, let's soften the view even more. Imagine you are very far away safe and still looking toward a black hole that sits against a background full of stars. The stars behind it are not affected because the black hole is reaching out. They are affected because their light passes through curved space on its way to you. Some starlight that would have missed your eyes is bent toward you instead. Some that would have reached you is bent away. So the star field looks subtly rearranged. A star might appear slightly displaced. A faint arc might appear where no arc was before. In special alignments, a distant star's light can be bent into a partial ring, a gravitational lens, like a halo drawn by geometry. This is not the black hole emitting anything. It is the black hole shaping the paths that light can take. In a calm way, it is like watching water flow around a stone in a stream. The stone does not chase the water. It simply changes the shape of the flow, and the flow reveals the stone. So when you hear someone say, black holes distort the view of space, you can hold it as something quiet. A curvature that redirects paths. A heavy object that reshapes how the sky arrives to your eyes. If you have ever looked through a glass sphere and seen the world behind it warp, you already have a gentle intuition for gravitational lensing. The sphere does not create new scenery. It bends the paths of light from what is already there. Now, with black holes, there is one more delicate layer that makes the images so iconic. Light can orbit. This does not mean a beam of light becomes a tiny planet. It means that near a black hole, there is a region where the curvature is so strong that certain paths loop around the hole before escaping. A photon, a particle of light, can skim around the black hole circlet once or more, then once, and then finally find a way out. Every time it loops, its path lengthens. And the longer the path, the more chances it has to reach you from multiple directions. This creates what is sometimes called the photon ring. Think of it as the echo of light. Light that has taken the long way around light, that has wandered near the edge and returned, bringing the signature of extreme curvature with it. This is why the ring can look so sharp, so precise, so strangely clean. It is not an artistic exaggeration. It is a natural feature of how curved space organizes the light that escapes. If any of this feels like too much to hold, let it simplify again. A black hole is seen by the glow of matter around it. That glow is shaped by motion and heat. and gravity bends the light into a ring-like view that looks almost symbolic, even though it is just physics. Now, you might wonder how we could ever see something so distant and so small on the sky. This is where the story becomes quietly impressive. When astronomers produced the famous image of a black hole's shadow, they did not use a single camera. They used a planet, not literally the whole planet, but a network of radio telescopes spread across Earth, working together as if they were one instrument. By combining signals from telescopes separated by thousands of kilometers, they achieved the resolution needed to see the shape near the event horizon. This technique is called very long baseline interferometry. You do not need the name, just feel the idea. Many far apart listeners all hearing the same faint whisper and then combining their hearing to form a clearer picture. It is a beautiful kind of collaboration. And it is also a reminder that black holes are not beyond science. They are difficult, yes, but they are not magic. They leave measurable fingerprints. Even when we cannot form an image, we can still detect black holes by how they influence their surroundings. Sometimes we see stars orbiting something invisible. A star moves in a path that reveals a hidden mass. The star's orbit tells us how heavy the central object must be. If there is no visible star there, and no cloud of ordinary matter could remain stable at that density, then a black hole becomes the simplest explanation. This is how we know about the supermassive black hole at the center of our own galaxy. We watch stars near the galactic center trace their orbits over years. Their paths are not guesses. They are measured. And the measured mass that holds them in those orbits is compact and dark. Sometimes we detect black holes through X-rays. In a binary system, a black hole can orbit a companion star. Gas from the star can be pulled toward the black hole, forming a hot disk. The inner region of that disk becomes so hot that it emits X-rays. Those X-rays can reach our telescopes, telling us that something is feeding, something is heating, something is spinning close to an extreme gravitational well. Sometimes we detect jets. In some systems, magnetic fields near the disk can launch streams of plasma outward at high speed. These jets can shine in radio waves and other wavelengths, and their presence can mark an active black hole at the center of a galaxy. But notice what all of these methods have in common. We see the neighborhood. We see the effects. We see the glow of infalling matter, the pull on nearby stars, the bright whisper of high-energy radiation, the long lines of jets. We do not see the black hole itself as an object with a surface. A black hole is defined by a boundary, not by a wall. So when you imagine it, do not imagine a cosmic tunnel or a hole punched through reality. Imagine a region where the usual routes outward no longer exist, and outside that boundary, the universe can still be luminous and structured because matter can orbit without falling in, and light can still escape if it starts from the right side of the shoreline. This is one reason black holes can feel strangely calming when you meet them with the right frame. They are extreme, but they are not chaotic in the way our anxious minds sometimes picture. There is another quiet correction that helps. People sometimes imagine black holes as vacuum cleaners sucking everything in from afar. Black holes do not suck in everything, but gravity does not work like a mouth with reach. A black hole's gravity at a distance behaves like the gravity of any object with the same mass. If you replaced our sun with a black hole of the same mass, the planets would orbit in nearly the same paths. The sunlight would be gone, yes, and Earth would become cold, but the orbital mechanics would remain similar. The black hole would not suddenly pull the planets inward just because it is a black hole. It would be the same mass shaping the same gravitational field far away. What changes is what happens close to it. Close to the black hole, the curvature becomes extreme. Close to the boundary, paths bend inward. Close to the center, our current theories reach their limits, but from far away, it is simply mass quietly shaping orbits. This is an important reassurance. A black hole is not a cosmic predator that can hunt you across space. It is a heavy, dark region that sits where it sits, and its strongest effects are local, not universal. So if you ever feel a flicker of fear, when you hear black hole, you can replace that fear with a more accurate picture. A black hole is a calm geometry, a boundary in space-time, a place where the rules become more intense, not a place where the rules disappear. Now, let's return to the image again, because your mind learns by returning. The ring of light you see in many depictions is not the event horizon itself. It is the glow of matter and the bending of light around the black hole. The dark center is not a picture of a hole you could fall into like a cave. It is the shadow created by the black hole's gravity, a region from which light cannot reach the observer along any path. The brightness around it can be asymmetric because the disk is moving and relativity changes how brightness is received. And the fine sharpness of the ring can be influenced by light that is looped around, bringing the signature of strong curvature. All of that is outside the boundary. All of it is still in the part of the story where information can reach us, which is comforting because it means our curiosity has a place to stand. We can stand outside and learn. We can let the black hole remain what it is and still understand its shape and its effects. Now let's pause and take a soft inventory so you do not have to carry too much forward. So far, we have not gone inside anything. We have simply looked from far away. We have seen that black holes are detected by their neighborhoods. We see hot matter spiraling in. We see light bent into rings and arcs. We see stars orbiting invisible mass. We see X-rays from heated disks. We see jets in some active systems. And we have corrected a common fear. A black hole is not a cosmic vacuum cleaner. From far away, it is mass like any other. Its most dramatic effects happen only near its boundary. If your mind wants to rest here, it can. You can picture that ring again. A quiet halo of light, like a thin bracelet suspended in the dark. You can picture the background stars subtly shifted, as if the sky is being viewed through curved glass. And you can picture yourself at a safe distance watching without urgency, because nothing about this requires action. This is a story of understanding, not a story of survival. In the next part of our journey, we will move from the visible ring to the invisible line. We will talk about the event horizon, the shoreline that defines a black hole, but we will carry only one simple idea forward. A black hole is known by what surrounds it, and even the strangest darkness in the universe can be traced gently by the light that almost escapes. Now, we move from the visible ring to the invisible line. So, what is a black hole really? In the last part, we stayed with what we can see from far away: a halo of light, a dark center, the sky subtly distorted as if gravity were a clear glass lens. All of that lives outside the defining boundary. The true definition of a black hole is not a disk or a jet or a bright ring. A black hole is a region of space where gravity is so strong that light cannot escape. Those are the neighborhood. The black hole itself is defined by a simple condition. There exists a boundary beyond which no signal can return. Physicists call this boundary the event horizon. It is not a wall. It is not a surface you could touch. It is not a physical shell made of matter. It is a line in the story of space and time. If you prefer a gentle picture, imagine a quiet shoreline at night. In the shallow water, a swimmer can still turn back. In deeper water, the current grows stronger. And there is a point where the current becomes so steady and so fast that turning back is no longer possible, no matter how calmly you try. The shoreline itself is not made of stone. It is a boundary in behavior. Outside, escape is possible. Inside, every path leads inward. That is the event horizon. To understand why this happens, we need one calm idea about gravity. Gravity is not only a force pulling things down. In Einstein's picture, gravity is geometry. Mass and energy curve space and time, and objects move along the straightest paths available within that curved geometry. In everyday life, those paths look like falling. A dropped cup follows a curve toward the floor. The moon follows a curve around Earth. Earth follows a curve around the sun. But the deeper truth is that motion is being guided by the shape of space-time. Near a black hole, that shape becomes extreme. Space is curved so strongly that what we call outward and forward begin to change meaning. Paths that would have led away bend back toward the center. Even light, which always travels at its own speed, finds its routes redirected. This is why a black hole is not really a hole. A hole suggests an absence, a missing piece. A black hole is not missing space. It is a region where space-time is curved in a particular way and where the future points inward. That phrase can sound strange, so let's soften it. Think about directions. Most of the time, you can choose to step north, southeast, or west. You can choose to stop. You can choose to turn around. But imagine being on a gentle moving walkway at an airport. If the walkway is slow, you can walk against it and return. If it speeds up, you might have to work harder. And if in some imaginary world, the walkway moved faster than you could possibly walk, then no matter what you did, your future steps would carry you forward with it. Inside the event horizon, forward in time is like that. It is not that you are being pulled by a monster. It is that every possible future path points deeper inward. This is why the event horizon is a one-way boundary. Outside the horizon, a light signal can be aimed outward and it will travel away. Inside the horizon, there is no outward aim that can lead to escape. Every direction you could send the signal eventually leads inward because the geometry has changed the landscape of possible paths. Now let's bring this back to something simpler and more familiar. There is a concept called escape velocity. Escape velocity is the speed an object would need to leave a gravitational field without falling back. On Earth, escape velocity is about 11 kilometers per second. That is fast, but it is still a number that belongs to rockets. Now, imagine increasing the mass of an object while keeping it compact. The gravity near it grows stronger. The escape velocity rises. At some point, the escape velocity at a certain radius would reach the speed of light. That radius is, in a simplified sense, the radius of the event horizon, because nothing can travel faster than light, and light itself would need to travel faster than light. To escape the boundary becomes absolute. This is the quiet logic. The horizon is where the required escape speed equals light speed. Outside, escape is possible. Inside, escape is not. But remember, this is not a literal surface. It is not like a lid on a container. It is a mathematical boundary in the behavior of paths. So, what happens if you fall toward the horizon? From your own perspective, nothing magical happens at the boundary. If the black hole is large enough, the tidal forces at the horizon can be mild. You would not necessarily feel a sudden tearing. You would simply continue carried by your own momentum and by the geometry of space-time. This is one of the strangest truths about black holes. The event horizon is dramatic to the universe, but it can feel uneventful locally. The drama is not in the sensation. The drama is in the consequences, because once you cross, you can no longer send information back out. Now, from the perspective of a distant observer, the story looks different. If someone watches you fall toward the horizon from far away, they will see your light signals slow and redden. Your clock will appear to run more slowly. Your image will dim. And in a simplified description, you will appear to approach the horizon and never quite cross it. This is not because you are literally frozen in place. It is because the light that carries information about you is taking longer and longer to climb out of the gravitational well. And it is losing energy as it does. So the observer sees a slow fade. From your own point of view, you pass through. From far away, you fade near the edge. Both views are consistent because they describe different frames of reference in curved space-time. If you are listening for sleep, you do not need to resolve every detail of this. It is enough to feel the shape, a boundary that is not a wall, a crossing that is normal locally, a one-way rule for information. That is what makes a black hole a black hole. Now, let's address one of the most common mental pictures people carry, the picture of a black hole as a hungry vacuum cleaner. It is not accurate. A black hole does not have a special sucking power at long range. It has gravity, and gravity depends on mass and distance. Far from a black hole, its gravitational pull is the same as the pull of any other object with the same mass. If the sun were replaced by a black hole of one solar mass, Earth's orbit would remain nearly the same. We would be cold and dark, yes, but the orbit would not spiral inward just because the central object is a black hole. The difference is near the boundary. Near the black hole, the required speed to escape grows enormous. Near the horizon, light cannot leave. Near the center, our current theories become incomplete. But at distance, gravity behaves in familiar ways. This matters because it removes a hidden fear. Black holes are not wandering traps that can suddenly pull in a galaxy from the other side. They are local extremes. They influence what comes close. They shape what orbits near. They do not reach across the universe with extra hunger. Now let's deepen the definition in a gentle way. When we say no, signal can escape, we mean no information can be carried from inside the horizon to outside. Information can ride on light. It can ride on radio waves. It can ride on any particle moving outward. But inside the horizon, there is no outward route. This is why black holes are not just dark objects, but information boundaries. Outside, the universe can know what is happening. Inside, the universe cannot receive updates. This is a profound idea, but it can also be calming. It means that the black hole is not a chaotic hole-ripping reality. It is a region with a clean rule, a clean boundary. Now what about the bright ring and the disk we saw before? Those are outside the horizon. Most of the light we see from black hole systems comes from matter that has not yet crossed. It is circling. It is heating. It is radiating. Some of it will fall in. Some of it will be flung outward. Some of it will join a jet. But the glow we see is largely the story of the outside. In fact, the most luminous black hole systems are often the ones actively feeding, because the disk becomes bright. A black hole itself is dark. A black hole with a bright disk can look like a lighthouse. The darkness and the brightness are not contradictions. They are different parts of the same system. Now, it helps to understand another quiet term, the Schwarzschild radius. This is the radius associated with the event horizon for a non-rotating black hole in the simplest model. It scales with mass, double the mass, double the radius. This is why larger black holes have larger horizons, and this leads to a comforting point about scale. A small black hole can have extreme tidal forces near its horizon. A very large black hole can have gentler tidal forces at the horizon because the horizon is farther from the center where gradients are less steep. So crossing the horizon is not automatically a violent experience. It depends on the mass. This is one reason supermassive black holes can sit at the centers of galaxies without shredding everything nearby. Stars can orbit at safe distances. Gas can circle. A whole galaxy can exist around a central black hole for billions of years. The presence is heavy. The structure is stable. Again, we replace the fear story with a structure story. Black holes are not cosmic jaws. They are deep wells in the geometry of space-time. Now let's pause and make the definition feel even simpler. A black hole is a region of space-time where gravity is so strong that there is an event horizon, a boundary beyond which nothing can return. If there is no horizon, then it is not a black hole, even if it is dark. If there is a horizon, then it is a black hole, even if there is no disk and no ring. So the horizon is the defining feature. Everything else is optional scenery. This helps us understand why black holes can come in different sizes and environments. A black hole formed from a dying star can be alone drifting through the galaxy, quietly, almost invisible. A black hole in a binary can be bright in X-rays because it is feeding. A supermassive black hole in a galactic center can be calm for long periods, then become active if a supply of gas arrives. The horizon remains the same kind of boundary in all cases. Now, if your mind is still with the imagery, you can picture the horizon as a soft edge, not a hard cliff. There is no glowing line you can see. There is no signpost in space saying here is the point of no return. It is simply a place where the geometry crosses a threshold. That threshold is defined by escape paths. Outside, there exist paths that lead outward. Inside, there do not. And this is where we can add one more gentle clarification. When we say light cannot escape, we do not mean light slows down below its speed. Light still moves at light speed locally. The physics of light remains consistent. What changes is the shape of space-time through which it travels. If you roll a marble across a gently curved surface, it can roll outward. If the surface becomes a deep funnel, the marble might circle and spiral inward. The marble is not choosing differently. The surface has changed the available paths. Light follows the available paths. So at the horizon, and inside the available outward paths, no longer lead outward. This is why the horizon is so clean as a concept. It is not a place where physics becomes random. It is a place where geometry becomes decisive. Now let's gather this layer in a calm summary, the way you might fold a blanket. We started with what we can see, a ring of light, a shadow. Now we have named the core definition. The black hole is the horizon, a one-way boundary for signals, a region where the future points inward. We have also cleared away a common misconception. A black hole does not suck at long range. Its gravity far away is like any mass. Its extremes are local near its boundary, and we have softened the picture. The event horizon is not a wall. It is a mathematical boundary. Crossing it is not necessarily dramatic in sensation. The drama is in what can be communicated afterward. If you are drifting, you can let the details blur now. Just hold the image of a shoreline. Outside the shoreline, the ocean still exchanges waves with the land. Inside the boundary, the current flows one way. The horizon is like that. And if that feels strange, it is also quietly beautiful. Because it means the universe can have boundaries that are not made of matter. Boundaries made of rules. In the next part of the journey, we will explore one of the most famous consequences of those rules, time. We will see how gravity can stretch time near a black hole and why different observers can honestly experience different rates of passing moments. But for now, we rest in the simplest definition. A black hole is not a hole you could fall through into nowhere. It is a region of curved space-time with a horizon beyond which light cannot return. And you listening here are far outside any such boundary, safe, still, free to let your eyes close as we move on. Now, we come to the part that people often describe with dramatic words: time near a black hole. Does time slow down near a black hole? In other videos, time is used like a jump scare. It is framed as a cosmic horror, as if the universe is trying to break your sense of reality. Tonight, we will hold it differently. Time near a black hole is not a threat. It is one of the clearest ways the universe shows that it is consistent even under extreme conditions. If you are comfortable, let your breathing slow a little. Let your mind imagine this as a gentle experiment, not an emergency. We will stay safely at a distance, and we will use imagination the way a scientist uses a diagram. Not to frighten, but to clarify. To begin, let's soften the word time. In daily life, time feels like one smooth river. The same for everyone. A minute is a minute. A second is a second. But in Einstein's view, time is not separate from space. They are woven together into one fabric space-time. And gravity is not just a pull through space. Gravity is a curve in that fabric. When the fabric curves, distances change, paths change, and the pace of time can change too. This is called gravitational time dilation. It means time runs differently near a black hole compared to far away. It means that clocks run at different rates depending on how deep they are in a gravitational field. You have already lived with this in a small way without knowing it. A clock at sea level ticks a tiny bit more slowly than a clock high on a mountain because gravity is slightly stronger, closer to Earth's mass. The effect is extremely small for us, but it is real. And it has to be accounted for in systems like GPS. So the idea is not exotic. It is a normal feature of nature. Near a black hole, the same feature becomes stronger. Imagine two observers. One stays far away from the black hole in a region where gravity is gentle. The other drifts closer, hovering near the edge near the event horizon. Both observers have hearts that beat. Both have clocks that tick. Both feel time passing normally in their own bodies. This is important. In your own frame, your time always feels like time. The strangeness appears when you compare. The observer far away looks toward the one near the black hole. They receive light signals, and those signals carry information about the near observer's clock. And they see something remarkable. They see the near observer's clock running more slowly. A second for the person near the black hole appears longer to the person far away. The closer the near observer is to the horizon, the more pronounced the slowing appears. If the near observer sends a pulse of light once every second, the far observer receives those pulses less and less frequently stretched out in time. This is not because the near observer is literally moving in slow motion. It is because the light carrying the signals has to climb out of the curved space-time near the black hole, and in climbing, it loses energy. That loss of energy shows up as a shift in the light. The light becomes redshifted. Its wavelength stretches to longer, softer colors. Its frequency decreases. The signal weakens, So to the distant observer, the near person appears to slow and dim as they approach the horizon. If you want a gentle image, you can picture it like a lantern being lowered into a deep well. The lantern still burns normally down there, but the light that reaches you at the top becomes fainter, and the timing of its flicker becomes slower because the path is longer and the climb is harder. Now, what does the near observer experience? If you are the one drifting near the horizon, you still feel your seconds ticking normally. Your breathing still rises and falls in the same rhythm. Your thoughts still arrive at the same pace. You do not suddenly feel time turn thick like syrup. Time is local. You always carry your own clock with you. So where is the strangeness? The strangeness lives in the comparison between two different gravitational environments. Both experiences are real. Both are honest. And this is the heart of relativity. Time is not a single universal metronome. It is part of the geometry, and different observers can measure it differently, especially near extreme gravity. Now, there is a classic phrase people use. They say someone falling toward a black hole appears to freeze at the horizon. This phrase is a simplification. It describes what the distant observer can see, not what the falling person experiences. From far away, the image of the falling person becomes more and more delayed. The light signals take longer to escape. The redshift grows stronger. The image grows dimmer, so the distant observer never sees a clear moment of crossing. They see an endless approach and a fade, but for the falling person, there is a crossing. If the black hole is large enough, they can pass the horizon without any sudden local drama. They continue inward because their future paths point inward. These two stories can both be true because they are stories told in different frames. If that feels strange, you do not need to solve it like a puzzle tonight. You only need to feel the shape. From far away, the universe cannot easily receive updates from near the horizon. From close up, the journey continues normally step by step, moment by moment. Now, there is another gentle point that makes time near a black hole feel even more beautiful. Time dilation is not only about watching someone else slow down, it is also about the way the universe lays out its structure. In curved space-time, there is no single agreement on what now means across large distances. There are different slices of time, different ways to define simultaneity. This is not chaos, it is geometry. If you have ever tried to draw latitude and longitude lines on a sphere, you know that the lines curve and converge near the poles. What looks straightforward on a flat map becomes subtle on a curved surface. Space-time is like that. Near a black hole, the curvature becomes so strong that the simple flat map intuition breaks. And this is where we can bring back the image of the ring from earlier. The ring of light around a black hole is a visual signature of curved space. Time dilation is a temporal signature of the same curvature. They are two expressions of one underlying reality. Space bends, time bends with it. Now let's add one more quiet layer. Not all black holes treat time the same way in detail. A rotating black hole, which is likely the common case in nature, introduces another effect called frame dragging. Rotation drag space-time around with it like a slow whirlpool in the fabric. This is not something you need to calculate. Just picture it softly. A massive spinning object, not only curving space-time inward, but also gently twisting the surrounding geometry. Near such a black hole, the paths of matter and light can be influenced by this twist. Orbits shift. The region where stable orbits exist changes, but the central time story remains the same. Deeper gravity means slower clocks when compared with clocks far away. Now, if your mind is wondering why this matters beyond the beauty, it matters because time dilation has been measured. We measure it around Earth. We measure it near the sun. We measure it in the behavior of particles. And in the most extreme environments, we expect it to play a major role in how energy is released from accretion disks and how signals leave black hole neighborhoods. This is not a fantasy. It is one of the best tested ideas in physics, simply extended into a place where gravity is strong. So when you hear dramatic claims, you can replace them with a calmer truth. Time near a black hole behaves differently, not because the universe is breaking, but because the universe is consistent. The rules are being followed in a deeper curve. Now let's gather the feeling into a single soothing picture. Imagine two clocks. One is in your room, with you ticking softly. The other is far away near the edge of a black hole, ticking softly too. Each clock believes it is normal, and each is right in its own place. The difference appears only when you compare them, when light carries information across the curved geometry. From far away, the near clock looks slower. Its signals arrive stretched and reddened like a lullaby played from a distance through thick air. From close-up, time remains personal and steady moment by moment. This is not a reason to be afraid. It is a reason to feel a quiet awe, because it means the universe is not just a stage where things happen. It is a structured fabric where the pace of happening is part of the shape. If you are tired, you can let the technical words drift away now. Just keep the calm core. Gravity curves space-time. Near a black hole, the curve is strong. When you compare clocks at different depths, they do not match. And still nothing about that threatens you here. You are far from any event horizon. Your clock is ticking in the gentle gravity of Earth. Your minutes are ordinary, and that ordinariness is a gift. In the next part of our journey, we will step back from time and look at scale. We will see that black holes come in different sizes, born in different ways, living in different environments, and we will begin to understand why some of them grow to extraordinary masses, resting at the centers of galaxies like quiet anchors. But for now, let time soften. Let the thought of curved space-time be like a warm blanket around your mind. A universe that can bend. A universe that can stretch its moments. And you safe inside one steady slice of it, letting the night carry you toward rest. Now we step back. We have looked at the ring of light that can surround a black hole. We have traced the idea of an event horizon, a one-way boundary for signals. We have felt how time can stretch near deep gravity, and now we widen the view, because black holes are not all the same size, and they do not all live the same kind of life. In the same way that stars come in many masses and stages, black holes come in different kinds and scales. This is one of the most calming facts about them. A black hole is not a single mythic object. It is a category of objects defined by the presence of an event horizon, and nature can create that horizon in more than one way. We can begin with the smallest common kind and move outward like ripples. The first kind is the stellar mass black hole. These are black holes born from stars. When a very massive star reaches the end of its life, it can no longer support its own weight. Its core collapses. In some cases, the collapse triggers a supernova, an explosion that throws the star's outer layers into space. In other cases, much of the star can fall inward more directly. What remains can be a neutron star, or if the core is heavy enough, a black hole. The black hole formed this way is usually a few times to a few tens of times the mass of our Sun. This is a small number compared to the black holes we will meet later, but it is still enormous for something that fits inside a region not much larger than a city. A stellar mass black hole is like a dense punctuation mark in space. It can drift quietly through the galaxy, almost invisible, unless it happens to interact with something. And this is an important point. Many black holes are quiet. A black hole does not automatically produce light. It produces light only if something is falling toward it and heating up. So a solitary black hole moving through thin interstellar space might be practically undetectable. But if it has a companion, the story changes. In a binary system, a black hole can orbit a normal star. If the star swells or sheds gas, some of that gas can be captured by the black hole's gravity. It spirals inward, forming a hot disk. The inner disk can become so hot that it emits X-rays bright and sharp, reaching us across the galaxy. In these systems, we often learn about the black hole by watching the dance. We measure the companion star's motion. We see it wobble. We infer the mass of the invisible partner. And when that mass is too large to be a neutron star, and no light comes from a solid surface, a black hole becomes the simplest explanation. So stellar mass black holes are one family, small by black hole standards, born from dying stars, sometimes quiet, sometimes bright, depending on whether they are feeding. Now, between the stellar black holes and the giants, there is a category that is still being mapped. Intermediate mass black holes. These are black holes that might range from hundreds to hundreds of thousands of solar masses. They are not as common in our catalogs and not as easy to confirm, but there is growing evidence that they exist. They may form from the mergers of smaller black holes or from dense star clusters where repeated interactions and collapses build a heavier core. If stellar black holes are like punctuation marks, intermediate black holes are like small knots in the fabric of a galaxy, heavier than a single star's end state, but not yet the central anchor of a whole galaxy. They are an active area of research, and it is good for your mind to hear that. Science is not finished. The universe still has categories we are refining. Now we move to the giants, supermassive black holes. These live at the centers of galaxies. They are millions to billions of times the mass of the Sun. Our own Milky Way has one. It sits at the galactic center, quiet most of the time, holding a large mass in a compact dark region while stars orbit in complex paths around the central gravitational pull. A supermassive black hole is not the whole reason a galaxy exists, but it often sits in the heart of the galaxy's structure. It is like a deep weight at the center of a spinning system. And here is another calming correction. A supermassive black hole does not necessarily swallow the galaxy. Most stars are far away from the center. They orbit at distances where the black hole's gravity is simply part of the overall gravitational field of the galaxy, along with the mass of stars' gas and dark matter. The black hole is a central mass, not a galaxy-sized mouth. The most dramatic feeding happens when gas flows into the central region. When a supermassive black hole is actively feeding, the accretion disk can become incredibly luminous. In that phase, the galaxy can have a blazing core, a quasar, bright enough to outshine the surrounding stars. But even then, it is not a sign that the galaxy is doomed. It is a phase of growth and energy release. The black hole is converting gravitational energy into light. Matter falls inward. The disk heats. Radiation pours out. In some cases, magnetic fields help launch jets, long streams of plasma that extend far beyond the galaxy's bright core. Those jets can influence the galaxy's environment. They can heat gas, move gas, and change how easily new stars form. So a supermassive black hole can act like an engine in the life of a galaxy, sometimes quiet, sometimes loud, depending on what it is being fed. Now, why do galaxies have these giants at their centers? We do not yet have a single complete story, but there are strong ideas. In the early universe, galaxies were forming and merging more actively. Gas was abundant. Dense regions could collapse. Black holes could grow by feeding and by merging with other black holes. Over time, the central black hole and the galaxy can grow together, influencing each other through feedback, through energy exchange, through the slow shaping of structure. The details are complex, and different galaxies have different histories, but the broad picture is clear. Supermassive black holes are not rare anomalies. They are common features of galaxies. Now, at the far edge of scale, there are the extremes. Black holes so massive that the numbers begin to feel like fog. This is where names like TON 618 appear in the scientific record. TON 618 is not a black hole you need to fear. It is unimaginably far away, but it is useful as a signpost because it shows what is possible. There exist black holes that hold tens of billions of solar masses sitting in distant galaxies, shining in the past light. We receive not as threats, but as evidence. Evidence that nature can build truly enormous central masses. In a different episode, we can take TON 618 slowly and fully, because it deserves a dedicated journey. Tonight, we only use it as a quiet reminder. The category called supermassive includes a wide range. Some are a few million suns. Some are billions. Some may reach beyond that. The important feeling is not the exact number. The important feeling is that the same rule holds across all scales. A black hole is defined by an event horizon. Whether it is born from a single star or grown in the center of a galaxy, the defining boundary is the same kind of one-way line. The differences come from mass, and mass changes the size of the horizon and the environment around it. A larger mass means a larger horizon radius, double the mass, and the horizon radius roughly doubles in the simplest picture. This gives us an intuitive scaling. Small black holes have small horizons. Large black holes have large horizons, and the environment changes too. Small black holes often live in the stellar neighborhoods of a galaxy. They can be part of binary systems. They can merge, producing gravitational waves. Large black holes live in galactic centers. They influence gas flows, star formation, and sometimes produce quasars and jets. So we can summarize the family tree in a calm way. Stellar mass black holes, born from dying stars, usually a few to a few tens of solar masses. Intermediate mass black holes, a middle range still being mapped, likely formed through mergers and dense cluster dynamics. Supermassive black holes, millions to billions of solar masses, often at galaxy centers, sometimes quiet, sometimes luminous when feeding. And then the extremes, like TON 618, sitting near the upper edges of what we have found so far, reminding us that the universe has a broad range. Now there is one more subtle comfort in this scaling. The most frightening mental images people carry, the idea of being stretched and torn at the horizon, depend strongly on the mass. A small black hole can have strong tidal forces near its horizon because the gravity changes rapidly over short distances. A very large black hole can have gentler tidal forces at the horizon because the horizon is farther out from the central region where gradients become steep. So the edge of a supermassive black hole can be in a sense calmer than the edge of a small one, even though the black hole is far more massive. This is a quiet reversal of intuition. Big does not always mean more violent at the boundary. Big can mean the boundary is broader, smoother, less sharp in local sensation. Again, this is not an invitation to go near one. It is simply a way to replace fear with accurate structure. Now, if your mind is looking for a single thread to carry forward, here it is. Across all kinds and scales, a black hole is the same type of object, a region of space-time with an event horizon. Everything else is context, how it formed, what it is feeding on, whether it is alone or in a pair, whether it is quiet or luminous. Those are the different lives black holes can live. And the universe, like a patient storyteller, uses the same fundamental rule, then varies the setting. If you are sleepy, you can let the categories blur into a simple picture. Small black holes born from stars, large black holes grown in galaxies, a spectrum between them still being explored, and a few extremes far away showing the outer edge of possibility. In the next part of our journey, we will ask a gentle question. If black holes are not cosmic vacuum cleaners, and if galaxies can live with them for billions of years, then what do black holes mean for the universe? How do they shape the systems that hold them? Not as destroyers in a horror story, but as parts of a larger structure. We will keep the tone calm. We will keep the pace slow, and we will let the universe feel not threatening, but quietly organized, even in its strangest places. Now, we bring a quiet question into the light. If black holes are so extreme, why do they not break the universe? It is a natural question because the words we use around black holes often sound like disaster, collapse, point of no return, nothing escapes. Those phrases can make the mind imagine an unstoppable spreading darkness, as if one black hole could eventually swallow everything. But the universe does not work that way. A black hole is extreme at close range and ordinary at distance. That sentence is one of the calmest truths you can hold. A black hole changes the rules only near its boundary. Far away, it behaves like any other object, with the same mass-shaping orbits and motions in the familiar way gravity always does. So the first reason black holes do not break the universe is simple. Their reach is not infinite. Gravity weakens with distance, and most of the universe is very far away from any given black hole. Even inside a galaxy, most stars spend their lives at safe distances from the central black hole orbiting the galaxy's center of mass, along with billions of other stars. They are not being pulled inward like dust into a drain. They are in stable orbits, held in a gravitational balance that can last for billions of years. Black holes do not break galaxies by default. They are simply part of what a galaxy is. Now, the second reason is about feeding. A black hole can only grow by consuming matter, and matter is not automatically delivered. For a black hole to gain mass, something has to fall close enough to cross the horizon. That is not the most common fate for most matter in the universe. Most stars are far apart. Most gas is diffuse. Most orbits are stable, so black holes are not constantly eating. Many of them are starving in the sense that they are not actively accreting. Even the supermassive black hole at the center of our galaxy is quiet most of the time. It is there, heavy and dark, but it is not blazing as a quasar. It is not devouring the Milky Way. It is simply present. This is an important shift in tone. A black hole is not always an active engine. Often, it is a quiet anchor. Now, you might be thinking about the times when black holes do become bright and powerful. Quasars, jets. Those can sound violent, and in a local sense, they can be energetic. But even those are not the universe breaking. They are the universe processing energy. When matter falls inward, it releases gravitational energy. The infalling matter speeds up. It heats through friction and collisions. It radiates. This radiation can be enormous. It can be bright enough to outshine the galaxy's stars. But notice what that means. The energy is not being stored as an expanding darkness. It is being released as light. So a feeding black hole is not only a consumer, it is also a converter. It converts gravitational potential energy into radiation that escapes into space. And that radiation has consequences. It can heat nearby gas. It can push gas outward. It can change how easily new stars form. This is often called feedback. Again, you do not need the term. Just feel the meaning. The black hole is not only taking, it is also returning energy to its environment in the form of light winds and sometimes jets. This is one reason black holes can actually limit their own feeding. If a black hole becomes too active, the radiation and outflows can blow away the very gas that would have fed it. It is like a fire that consumes oxygen and then, in its intensity, pushes air away, making it harder for itself to keep burning. So black holes do not simply eat without end. They live in a balance with their surroundings. They can have active phases and quiet phases. They can flare and then settle. They can grow and then slow their growth. This is a steady kind of behavior, not a runaway collapse of everything. Now there is another calm point that helps. Space is vast. Even when galaxies merge and black holes eventually meet, the universe is not a crowded room. It is a sparsely populated ocean. Two galaxies can pass through each other and still have very few direct star-to-star collisions because stars are so far apart. Gravity reshapes orbits. Gas clouds, compressed star formation can increase, and eventually the central black holes can sink toward the merged center. This process takes time, millions of years, hundreds of millions, sometimes longer. Nature is patient, so even dramatic events on cosmic scales unfold slowly, not like sudden tearing. When two black holes finally merge, they can produce gravitational waves, ripples in space-time that travel outward at the speed of light. Those ripples can be detected by instruments on Earth. This is one of the most beautiful connections between the extreme and the gentle. A colossal event happening far away can leave a faint whisper we can measure here. But again, the universe does not break. It ripples, then it settles. Now let's return to the fear story one more time and replace it with the structure story. The fear story says, black holes are holes that spread, swallowing everything. The structure story says black holes are compact masses with horizons embedded in larger systems, often quiet, sometimes active, always governed by the same rules. Most of the universe is not falling into black holes. Most matter is in stable structures. Stars orbit in galaxies. Galaxies orbit in clusters. Clusters form filaments. And black holes are part of this architecture, not a flaw in it. In fact, you could say black holes are one of the ways the universe handles extremes cleanly. Instead of allowing matter to collapse into an endless chaotic pile, the universe forms a boundary, an event horizon, a region where the outside can remain orderly, even if the inside becomes inaccessible. That boundary acts like a kind of containment, not in the sense of a prison, but in the sense of a definition. It marks where the outside description remains useful. This is why black holes are not the universe breaking. They are the universe keeping its rules even under pressure. Now, if you are listening with a sleepy mind, here is the simplest comfort you can take. Black holes are rare in space compared to the vast distances between things. Their strongest effects happen close to them. They do not hunt across the cosmos. They do not swallow galaxies by default. And when they are active, they often shine, releasing energy outward rather than deepening darkness. So the universe remains luminous, stable enough for stars to burn for billions of years, stable enough for planets to orbit calmly, stable enough for you to be here, breathing quietly, while a story about black holes becomes something that can soothe you instead of scare you. If any thought still feels sharp, let it soften into one image. A black hole at the center of a galaxy is like a deep weight in a spinning system. Not a mouth, but a mass. Not a threat, but a part of the structure. Around it, stars continue their long orbits. Gas moves in slow tides. the galaxy turns, and in your small room, far from any horizon, the night remains gentle and ordinary. In the next part of our journey, we will touch the edge of what we do not yet know, because even a calm story can make room for mystery. But we will carry this steady truth with us. Black holes are not the universe breaking. They are the universe being consistent even at its most extreme. Now we arrive at a softer edge. Everything we have explored so far lives in the part of black holes we understand reasonably well. The outside, the boundary, the way gravity shapes motion and light. But there is a place where our maps fade, and it is important to say this gently. Not knowing everything is not a failure of science. It is one of its most honest features. So in this layer, we will talk about what we do not know about black holes, and why that uncertainty does not need to disturb your rest. We begin with the deepest unknown, the inside. According to our best current theories, matter that falls past the event horizon continues inward. As it falls, it becomes denser. The equations we use predict that density keeps increasing until it reaches something called a singularity. A singularity is not a place we can picture. It is a signal. It tells us that our current description has reached its limit. When equations give infinities, it usually means the model is being pushed beyond where it applies. It does not necessarily mean that nature itself contains literal infinities. It means we need a deeper theory. So, when you hear the word singularity, do not imagine a physical needlepoint drilling through reality. Instead, imagine a blank spot on a map marked with a careful note. Here our tools stop working. That is the first unknown. What truly happens at the center of a black hole? We do not know, and that is okay. Now let's step back slightly to another question that often feels unsettling. What happens to information? In physics, information is not just data on a hard drive. It is the complete description of a system, the positions and motions of particles, the quantum states that define what exists. According to quantum mechanics, information is not supposed to be destroyed, but a black hole seems to hide information behind the event horizon. And when black holes slowly evaporate over enormous spans of time, a process predicted by quantum effects, it raises a question. Where does the information go? This is known as the black hole information problem. It is not a riddle meant to scare you. It is a technical tension between two very successful theories. General relativity describes gravity and space-time. Quantum mechanics describes particles and probabilities. Both work extremely well in their domains. Black holes sit at the intersection. They are places where gravity is strong and quantum effects matter. So when the theories disagree or become incomplete, it is not chaos. It is a signpost. It tells physicists where the next layer of understanding must be built. Many ideas exist. Some suggest that information is somehow encoded on the event horizon itself, spread thinly like a hologram. Others suggest subtle correlations in the radiation that escapes over time. Others explore deeper changes in how space-time itself is structured at the smallest scales. None of these ideas have been fully confirmed yet, and that is okay, because nothing about this uncertainty affects the calm structure of the universe you live in. Black holes do not behave unpredictably on human scales because of this mystery. Stars do not suddenly vanish. Galaxies do not unravel. The uncertainty lives in a realm far removed from daily life. Now let's talk about another unknown that often gets dramatized. What happens if you fall into a black hole? This question is usually framed in violent imagery, but in science, the honest answer depends on the size of the black hole and the path taken. For a small black hole, tidal forces near the horizon can be strong. For a very large one, those forces can be mild at the horizon. But here is the key point. No one can test this directly. It is not an experiment we plan to run, so the details of the subjective experience remain theoretical. This is not a failure. It is a boundary between imagination and measurement. Science is careful about that boundary. It tells stories where it can test them, and where it cannot, it stays tentative. That restraint is a form of respect for reality. Another unknown sits at an even more abstract level. How exactly do gravity and quantum mechanics fit together? Black holes tell us that our current theories are incomplete when pushed to extremes. They do not tell us that the universe is broken. They tell us that our description is unfinished. This is an important emotional distinction. An unfinished map invites curiosity. A broken map invites fear. Black holes invite curiosity. Now, let's talk about Hawking radiation, because it often sounds unsettling at first. Quantum theory predicts that black holes are not perfectly black. Over extremely long timescales, they can emit a faint radiation and slowly lose mass. For stellar and supermassive black holes, this process is incredibly slow, longer than the current age of the universe by many orders of magnitude. So while Hawking radiation is conceptually important, it is not a practical concern. Black holes are not about to fade away tomorrow. Again, this uncertainty lives far beyond your night. Now let's step back and look at all of this together. What do we not know? We do not know the true nature of the singularity. We do not know exactly how information is preserved or transformed. We do not yet have a complete theory that unites gravity and quantum mechanics. What do we know? We know how black holes form. We know how they influence their surroundings. We know how they bend light. We know how time behaves near them. We know how they fit into galaxies. We know how to detect them indirectly and increasingly directly. So the unknowns sit inside a strong framework of knowledge. They do not undermine it. They enrich it. Now here is the calmest truth of all. Every deep field of science has edges like this. There was a time when we did not know what powered the sun. There was a time when atoms were mysterious. There was a time when the nature of light itself was unclear. Uncertainty did not mean danger. It meant discovery was still ongoing. Black holes are not a sign that reality is fragile. They are a sign that reality is layered, and each layer reveals itself when the previous one is understood well enough. If you feel any lingering tension, let it settle into this image. Imagine knowledge as a shoreline at night. Behind you is solid ground, well mapped and familiar. Ahead of you is dark water, not because it is threatening, but because it is deep. You do not need to swim into it tonight. You can simply stand where you are feeling the steadiness of the land beneath your feet and knowing that the water will still be there tomorrow and the day after, waiting patiently for understanding. Science does not rush. The universe is not in a hurry, and neither are you. So, when you hear that, we do not know everything about black holes, let that thought soften. Not knowing is not a crack in reality. It is the open space where future understanding will gently form. And for now, the universe remains stable structured and kind enough to let you rest inside it. In the final part of our journey, we will gather everything we have touched into a single quiet picture and then let the story fade the way starlight fades at dawn. No urgency, no cliff, just a calm return to rest. Now we let the facts rest. We have built the shape of the story, the ring of light, the invisible boundary, time stretching in deep gravity, different scales, different lives, and the gentle edge of what we do not yet know. You do not need to hold any of it. In this part, we will simply drift. Let the room around you soften at the edges. Let the sound of my voice be a quiet tide. If your thoughts wander, that is fine. If you fall asleep, that is perfect. Imagine you are far from everything busy, far from headlines, far from the fast, bright world. You are in a calm place where the sky is dark and open. Somewhere in that dark, unimaginably distant, there is a black hole, not as a threat, not as a mouth, just as a shape in the universe, a place where gravity is deep enough to draw a boundary. If you picture it from far away, a soft circle of darkness as clean as an ink stain on velvet. Around it, a thin ring of light like a bracelet suspended in the night. The ring is made of matter in motion, gas and dust that once drifted quietly between stars has begun to spiral. It circles and circles, warming as it rubs, glowing as it heats. The light is not loud. It is a quiet glow that happens because the universe allows motion to become warmth and warmth to become light. Now imagine the light leaving the disk. Most of it moves outward, freed into space, traveling for years, for centuries, for millions of years. Some of it bends. It passes close enough to the black hole that its path curves, and the curve brings it around, as if the sky itself were a lens. Light that began on the far side can arrive to you from the near side because space-time is folded in a gentle arc. The ring appears not because the black hole emits it, but because gravity shapes what escapes. If you like, you can picture that curvature as a slow, invisible hand, not grabbing, not pulling, just shaping, like a river shaping its own banks. And in the center, there is the shadow, a region from which no light reaches you, not a void cut out of the universe, a shadow cast by geometry, a silence in the paths light can take. Now, let the idea of the event horizon enter gently. The horizon is not a line you can see. It is not a wall. It is a change in what is possible. Outside it, there are routes outward. Inside it, every route leads inward, a shoreline in space-time. If you imagine standing near a shoreline at night, you can feel the calm of a boundary. Land here, water there. You do not need to cross it. You do not need to test it. You can simply know. It exists cleanly, separating two kinds of motion, The event horizon is like that, a boundary that does not need to be dramatic to be absolute. Now let time soften. Time near the horizon is not a horror. It is a gentle stretching of the world's rhythm. A clock far away ticks steadily. A clock close to the horizon ticks steadily too. Both clocks feel normal where they are, but the space between them is curved. So, when signals travel across that curve, the rhythm changes. The distant clock hears the near clock as slower. The near clock continues without noticing anything strange. Two honest realities braided by geometry. If you let this idea settle into your body, it can become calming, because it means the universe is consistent. Even in deep gravity, it does not abandon its rules. It follows them more fully. Now, let the categories of black holes drift into a single spectrum. Small black holes born when stars collapse at the end of their lives. Quiet travelers in a galaxy, sometimes invisible, sometimes bright if they are fed. Black holes in pairs orbiting, merging, sending ripples through space-time that cross the universe like silent waves. Larger black holes in the centers of galaxies, deep anchors around which stars orbit for billions of years, sometimes quiet like a sleeping engine, sometimes luminous if gas falls inward and heats into a shining disk. And then far away the extremes, black holes so massive that the numbers feel like mist. They exist not to frighten you, but to widen your sense of scale. They remind you that the universe has room to be enormous without being unstable. If you ever hear a name like Ton 618, you can let it be only this: a sign that there are places where gravity has gathered into a vast, quiet weight. A reminder that the cosmos is wide enough to hold extremes without collapsing into chaos. Now let the question of why soften too. Black holes do not break the universe because their power is local. They are intense up close and gentle at distance. They can sit inside galaxies for ages, not as destroyers, but as parts of structure. When they are active, they often shine. They return energy outward. They heat and shape their surroundings, sometimes limiting their own growth by pushing gas away. A balance, a rhythm. Nothing about this requires fear. It is simply the universe being itself. Now, we come again to the edge of the unknown, the inside of the horizon, the place where our current maps fade. You do not need to enter it in your mind. You can stand outside it in the part of the story where light still escapes. The unknown does not have to feel like darkness. It can feel like depth, a deep ocean beyond the shoreline. Not dangerous from where you stand, just deep. A place where future understanding will one day glide slowly, carefully, without urgency. You can let that be enough. Now, if your thoughts are still racing, here is a simple permission. You do not need to solve the universe to rest in it. You do not need to hold every idea. You do not need to keep track of the map. You can let the story become a background hum, a ring, a boundary, a slow stretching of time, a quiet structure in a spinning galaxy, and you safe in your small corner of Earth, breathing in a steady rhythm. Imagine your breath as its own kind of orbit, in and out, a gentle loop that returns. Nothing demanding, nothing urgent, just motion returning to itself. If it helps, you can imagine the black hole's environment as a slow dance. Gas spiraling, warming, glowing, light bending, looping, escaping. A boundary holding its clean rule, time stretching near deep gravity, then returning to the ordinary pace far away. Everything moving, but nothing rushing. The universe does not chase you. It does not lean into your room. It stays out there, vast and quiet, while your life stays here, held by familiar gravity, familiar air, familiar night. Now, let the imagery drift into something even softer. A lantern in the dark, not harsh, not bright, just steady. The lantern is the accretion disk's glow far away, wrapped around a silence. The silence is the shadow calm and round. And around both, there is the larger darkness of space, not empty, but spacious. If you imagine stars behind it, imagine them gently displaced by lensing, not chaotic, just slightly shifted, as if the universe is reminding you that even light takes curved paths when it travels through deep gravity. And still the stars shine. Still the galaxy turns. Still you can rest. Now we let the story become simpler still. A black hole is a place where the universe draws a boundary. Outside information can travel. Inside, it cannot return. Everything else is detail. Beautiful detail, but not something you need to carry tonight. So you can let those details fall away one by one. Let the ring fade. Let the math fade. Let the questions fade. Keep only the feeling of a structured cosmos, a cosmos that can be strange without being threatening, a cosmos that can be deep without being cruel, a cosmos that can hold a circle of darkness and still be full of light. Now, if you are close to sleep, you can take one last permission. You have done enough by listening. You do not have to remember any words. You can let your mind float like a small boat on calm water and let the story pass beneath you. A quiet shoreline, a distant ring, a gentle bending of light, a slow stretching of time, and your breath returning again and again, steady, familiar, safe. In the next and final part, we will gather the journey in a few soft lines and then let it end without a sharp edge. For now, rest. Let the universe be large. Let your world be small. Let the night be kind. Now, we gather the journey in one quiet view, and then we let it fade. Tonight we met a black hole without fear and without rushing. We began from far away, where a black hole is not something you see directly, but something you understand through what surrounds it. A thin ring of light made by matter, spiraling and warming as it falls. A dark center, not a hole punched through the universe, but a shadow shaped by gravity, a region where light cannot find a path back out to us. We name the boundary that defines it. The event horizon, not a wall, not a surface, not a hard edge you could touch, but a change in what is possible. Outside it, there are routes outward. Inside it, every path leads inward, a quiet shoreline in space-time. Then we let our curiosity touch time. We saw that time is not a single universal river that flows the same everywhere. It is part of the fabric, and in deep gravity, that fabric curves. And the pace of time can differ when you compare clocks in different places. Near a black hole, the universe does not become chaotic. It becomes consistent in a deeper curve. We widened the view to scale. We saw that black holes come in different kinds, born in different ways. Some are born from the collapse of massive stars, small by cosmic standards, quiet travelers in a galaxy. Some may sit in the middle range, still being mapped by research. And some are giants resting at the centers of galaxies, shaping their environments over long spans of time, sometimes quiet, sometimes luminous, depending on what they are fed. We also took a calm look at what we do not yet know, the inside of the horizon, the deepest details of how gravity and quantum physics meet, the question of information. And we held those unknowns gently, not as reasons to worry, but as signs that discovery continues slowly, patiently, the way it always has. If you remember only one thing from tonight, let it be this. A black hole is not a monster. It is a region of space-time where gravity is strong enough to draw a boundary, and beyond that boundary, light cannot return. And you listening here are far outside any such boundary. You are in the gentle gravity of Earth. The air around you is ordinary. The night is ordinary. And there is a deep comfort in that ordinariness, because it means the universe can hold extremes without threatening your rest. If you feel your mind still holding on to details, you can let them go now. You do not need the ring. You do not need the horizon. You do not need the words. You can keep only a soft feeling, a vast structured cosmos, a quiet rule, a distant darkness wrapped in light, and your small, safe life here, sheltered by a planet that knows how to hold you. If you'd like, take one slow breath in and let it out without effort. Let your shoulders drop a little more. Let your face soften. Let your eyes rest. You have done enough by listening. And if sleep comes now, you can let it come. If you are still awake, and you feel like staying close to these quiet science journeys, you're always welcome to return. In future nights, we can take one part of this story at a time. We can visit the giants at the centers of galaxies. We can take a slow journey through the way black holes grow. We can explore the gentle physics behind the ring of light in more detail. And one night, if you want, we can travel to the far edge of scale, to an extreme black hole that helps the mind feel how wide the universe truly is. But you never have to chase any of it. These stories will be here when you want them. If you'd like to support this quiet kind of science, you're welcome to subscribe. And if this helped you feel calmer, you can save it for another night. Like a familiar path, you can walk again when the world feels too loud. For now, let everything drift away. Let the universe be large and distant. Let your room be small and safe. Let your breath be the only rhythm you need. A slow inhale, a soft exhale. Good night.